This is our prototype plug-and-play projector, alias PPP. We use a standard laptop to simulate the communication and computation unit to which the projector and the camera are connected. Here, we show our asynchronous distributed calibration process for a display made of 3 by 3 array of PPPs. To achieve this calibration, the array runs an SPMD program and generates a seamless image. The calibration has 3 steps: neighbor discovery, configuration identification, and alignment. Initially, all PPPs believe that they are alone in the environment and are solely responsible for displaying the whole image. Now, in the neighbor discovery step, each PPP projects a pattern with 4 colored grids. Each grid consists of a 5 by 5 array of square blobs. The PPP then captures the images of this pattern to discover all its neighbors and their relative positions. Communicating with neighbors via such camera image analysis is called sensor-based communication. At this point, each PPP, though aware of the existence of its immediate neighbors, is oblivious of the display configuration and its own position in it. Next, in the configuration identification step, binary coded bit patterns are embedded in the grids. These binary codes are used to convey each PPP's beliefs about where it is in the display and the total dimensions of the display. Every PPP starts by believing that it is the only node in a display of dimension 1 by 1. To illustrate this process, we show the decoded bit patterns in the text as well. Multiple rounds of sensor-based communication across adjacent projectors follow. Each node updates its own row and column, R and C, and the total rows and columns in the display, M and N. Update rules enable the diffusion of these parameters to all the nodes. We highlight the values of R, C, M, and N when they converge in each node. When all these parameters converge, we show the text done. The asynchronous nature of the method is illustrated by the random order of convergence. This is followed by a network communication step where each node gathers the IP addresses of all other nodes in the display. Now, each PPP knows their exact position in the display and hence is able to extract an appropriate part of the image. However, this image is not aligned geometrically or photometrically. Thus, if allowed to project an image, the display would now have noticeable seams. Next, in the alignment step, each PPP uses the blobs detected in the neighbor discovery step to compute the local homography between itself and its neighbors. The geometric alignment is then achieved by a distributed homography tree technique. This starts with the election of a PPP close to the center of the display as the root of the homography tree. All other PPPs align themselves with respect to this root. The homography tree is built in a breadth-first fashion using network-based communication. The process is initiated by the root. Each PPP sends its homography relative to the root to all its neighbors. The neighbors augment this with their local homographies. Thus, they generate their own homography to the root. This augmentation propagation continues until all nodes have computed their homography to the root. We illustrate this process by correcting an image projected by a PPP as and when it computes its homography. In this illustration, the middle node is chosen as the root. The projectors in the middle row and middle column are one step away from the root. Hence, they are the first ones to align. Next, the corner PPPs, which are 2 steps away from the root, also align themselves to the root. Thus, each PPP corrects its imagery geometrically and photometrically to create a seamless display. We demonstrate scalable and reconfigurable displays by showing dynamic addition and deletion from a calibrated display. We start with a 2 by 2 display and add 2 projectors to its left. Using their sensors, the neighboring PPPs can detect the addition and broadcast the information to all other PPPs. Then, all of them switch to the calibration phase and reconfigure to a 2 by 3 display. Similarly, we can add 3 more PPPs to generate a 3 by 3 display. Removal of projectors is achieved in a similar manner. However, after removal, some PPPs are deactivated to achieve a rectangular display. Here we demonstrate the removal of the top left PPP from a 3 by 3 display. To reshape this non-rectangular display, PPPs in appropriate rows and columns deactivate themselves and generate a rectangular 2x2 display. Our method can also tolerate some faults. In this illustration, the top left PPP fails during calibration. We detect this fault and reshape to a 2x2 display. Thus, our asynchronous distributed calibration enables truly scalable and reconfigurable displays.